Alexa, tell me a love story.
Starting Special Relativity and Classical Field Theory by Leonard Susskind and Art Friedman from Kindle. Read with Kindle Assistive Reader. There are 7 hours left in the book. In relativistic units, not only does c have a value of 1, but all velocities are dimensionless. For this to work out, we have to choose appropriately defined units of length and time. After all, velocity is a length divided by a time. If our time units are seconds, we choose light seconds as our length units. How big is a light second? We know that it's 186,000 miles, but for our purposes, that's unimportant. Here's what matters. A light second is a unit of length, and by definition light travels 1 light second per second. In effect, we're measuring both time and length in units of seconds. That's how velocity, a length divided by a time, gets to be dimensionless. When we use relativistic units, a velocity variable such as v is a dimensionless fraction of the speed of light. That's consistent with c itself having a value of 1. In a spacetime diagram such as Figure 1.2, the x and t axes are both calibrated in seconds. The trajectory of a light ray makes equal angles with the x-axis and with the t-axis. Conversely, any trajectory that makes equal angles with the two axes represents a light ray. In your stationary RF, that angle is 45 degrees. Knowing how to switch easily between the two types of units will pay off. The guiding principle is that mathematical expressions need to be dimensionally consistent in whatever system of units we're using at the time. The most common and useful trick in going from relativistic to conventional units is to replace v with vc. There are other patterns as well, which typically involve multiplying or dividing by some appropriate power of c, the speed of light. We'll show examples as we go, and you'll find that these conversions are fairly simple. Setting up our coordinates, again. Let's go back to our two coordinate systems. This time, we'll be very careful about the exact meaning of the word synchronous in the moving RF. In the stationary RF, 2 points are synchronous or simultaneous if they're both on the same horizontal level in a spacetime diagram. The 2 points both have the same t-coordinate, and a line connecting them is parallel to the x-axis. That much Newton would have agreed with. But what about the moving frame? We'll find out in a minute that in the moving frame the point x equals 0, t equals 0 is not synchronous with the other points on the x-axis, but with an entirely different set of points. In fact, the whole surface that the moving frame calls synchronous is someplace else. How can we map out this surface? We'll use the synchronization procedure described in a previous subsection, synchronizing our clocks, and further illustrated in Figure 1.2. Drawing a spacetime diagram is usually the best way to understand a problem in relativity. The picture is always the same. X is the horizontal axis, and t is vertical. These coordinates represent a RF that you can think of as stationary. In other words, they represent your frame. A line that represents the trajectory of an observer moving through spacetime is called a world line. With our axes in place, the next things to draw are the light rays. In Figure 1.2, these are represented by the lines labeled x equals ct and x equals minus ct. The dashed line from point A to point B in the figure is also a light ray. Back to the main road. Getting back to Figure 1.2, let's sketch in an observer Art, who's sitting in a railroad car moving to the right with constant speed v. His world line is labeled with equations that describe his motion. Once again, Art's frame will be moving such that x equals x minus vt, exactly like the moving observer in Figure 1.1. Now let's figure out how to draw Art's x-axis. We begin by adding 2 more observers, Maggie and Lenny. Maggie is sitting in the rail car directly in front of Art, to your right, and Lenny's rail car is directly in front of Maggie's. Adjacent observers are separated from each other by 1 unit of length as measured in your frame, the rest frame. Equations for Maggie's and Lenny's world lines are shown in the figure. Because Maggie is located 1 unit to the right of Art, her trajectory is just x equals vt plus 1. Likewise, Lenny's trajectory is x equals vt plus 2. Art, Maggie, and Lenny are in the same moving frame. They're at rest with respect to each other. Our first observer, Art, has a clock, and his clock happens to read 12 noon, just as he arrives at the origin. We'd assume the clock in the rest frame also reads 12 noon at this event. We both agree to call 12 noon our time 0, and we label our common origin with x equals 0, t equals 0 in your coordinates, and x equals 0, t equals 0 in Art's coordinates. The moving observer and the stationary observer agree by assumption on the meaning of t equals 0. For you, the stationary observer, t equals 0 all along the horizontal axis. In fact, that's the definition of the horizontal axis. It's the line where all times for the stationary observer are 0. Figure 1.2, SR frames using relativistic units is equals 1. The equations associated with Art are two different ways to characterize his world line. The dashed lines are the world lines of light rays. The constants 1 and 2 in the equations for Maggie's and Lenny's world lines are not pure numbers. Their relativistic units are seconds. Suppose Art sends out a light signal to Maggie from the origin. At some point, we don't know yet what that point is, Lenny will also send out a light signal toward Maggie. He'll somehow arrange to do this in a way that both signals reach Maggie at the same instant. If Art's light signal starts at the origin, Maggie will receive it at point A in figure 1.2. From what point must Lenny send his light signal, if it is to reach at Maggie at the same time? We can find out by working backward. The world line of any light signal that Lenny sends to Maggie must make a 45-degree angle to the x-axis. So all we need to do is construct a line at point A that slopes 45 degrees downward toward the right, and extend it until it crosses Lenny's path. This is point B in the figure. As we can easily see from the figure, point B lies above the x-axis and not on it. What we've just shown is that the origin and point B are simultaneous events in Art's frame. In other words, the moving observer, Art, will say that t equals 0 at point B. Why? Because in the moving frame of reference, Art and Lenny, who are equidistant from the central observer Maggie, sent her light signals that arrived at the same instant of time. So Maggie will say, you guys sent me light signals at exactly the same instant of time, because they both arrived here at the same instant of time, and I happen to know that you're at equal distances from me. Finding the x-axis. We've established that Art's, and Maggie's and Lenny's, x-axis is a line that joins the common origin, i.e., common to both frames, to point B. Our next task is to find out exactly where point B is. Once we figure out point B's coordinates, we'll know how to specify the direction of Art's x-axis. We'll go through this exercise in detail. It's a little cumbersome but quite easy. There are 2 steps involved, the first being to find the coordinates of point A. Point A sits at the intersection of 2 lines, the rightward moving light ray x equals ct, and the line x equals vt plus 1, which is Maggie's world line. To find the intersection, we just substitute one equation into the other. Because we're using relativistic units for which the speed of light c is equal to 1, we can write the equation x equals ct in an even simpler way. Substituting equation 1.5 into Maggie's world line, x equals vt plus 1 gives t equals vt plus 1, or t1 minus v equals 1, or even better. Now that we know the time coordinate of point A, we can find its x-coordinate. This is easily done by noticing that all along the light ray, x equals t. In other words, we can just replace t with x in equation 1.6 and write SAR equals 1/1 minus v. Voila! We found point A. With the coordinates of point A in hand, let's look at line AB. Once we have an equation for line AB, we can figure out where it intersects Lenny's world line, x equals vt plus 2. It takes a few steps, but they're fun, and I don't know of any shortcuts. Every line that slopes at 45 degrees, pointing downward to the right, has the property that x plus t is constant along that line. Every line sloping upward to the right at 45 degrees has the property that x minus t is constant. Let's take the line AB. Its equation is x plus t equals some constant. What is the constant? An easy way to find out is to take one point along the line and plug in specific values x and t. In particular, we happen to know that at point A, SAR plus TAR equals 2/1 minus V. Therefore, we know that this is true all along line AB, and the equation for that line must be x plus t equals 2/1 minus V. Now we can find B's coordinates by solving the simultaneous equations for line AB and for Lenny's world line. Lenny's world line is x equals vt plus 2, which we rewrite as x minus vt equals 2. Our simultaneous equations are x plus t equals 2/1 minus v, and x minus vt equals 2. The solution, after a bit of easy algebra, is: first, the most important point, TB is not 0. Therefore point B, which is simultaneous with the origin in the moving frame, is not simultaneous with the origin in the rest frame. Next, consider the straight line connecting the origin with point B. By definition, the slope of that line is TB/XB, and using x 1.8 we see that the slope is V. This line is nothing but the x-axis, and it is given very simply by the equation.
Alexa,
Keep in mind
stop.